Case Study Number 1, Hazard Characterization in Binder Jetting. Narrated by Rebecca Burton. There are 3 primary learning objectives for this module. At the end, the learner will be able to describe the process steps that make up binder jetting, identify the hazards that may be present during those tasks, and identify exposure controls that may be effectively used for those tasks. Binder jetting is an additive manufacturing method in which a liquid bonding agent is selectively applied to join fine particles in a powder bed, layer by layer. The printed part is then cured or sintered to evaporate the binder and fuse the powder particles into a single article. Binder jetting is typically used for prototyping or for producing custom parts, usually from metal, ceramic, or mineral powder. This process has several advantages for a creator. It allows for color printing and is generally faster than some other methods. The use of 2 materials, the powder and the binder, also allows for different combinations, which can be used to achieve a range of mechanical properties. Additionally, because the part is essentially submerged in the box of loose powder as it is built, this method does not require support structure to be designed in. This graphic shows the steps of the binder jetting process. The major steps related to potential exposure to health hazards during pre-printing are as follows. The powders are loaded into the printer. A roller rolls a layer of powder from the reservoir onto the build platform, and the print head applies 1 layer of binder. Then the binder is initially set by having an infrared lamp array passed over the layer of binder and powder. The build platform then lowers, the level of powder in the reservoir is raised up, and the process repeats until all layers have been printed. This produces a green part, the part made of powder fused together with binder, submerged in a bed of unfused powder. During post-printing, the green part in its box of powder is placed in an oven, usually overnight, where the application of heat cures the binder enough that the green part can be handled without breaking. Next, it has to be removed from the bed of loose powder. This is usually done either by digging the part out of the powder bed using a tool of some kind, or else using a vacuum of some sort to siphon the loose powder away from the green parts. Next, the harvested part is cleaned by having the loose powder blown off. This can be done in a glove box or something like a fume hood or a downdraft table, or simply out in the open depending on the particle size of the loose powder. After that, the green part is sintered in a furnace to remove the binder and fuse the powder material into a finished part. Sometimes the voids created by elimination of the binder are backfilled with a second material, such as bronze. Feedstock materials for binder jetting include metal powders, mineral powders, binders, and cleaner. Common metals include stainless steel, aluminum, copper, bronze, and mixtures of metals such as chromium or cobalt. Mineral or other powders could include compounds of silica or things like ceramic, gypsum, or glass. The binders are generally mixtures of solvents with other additives that help adhere the particles together. Binder jetting involves several hazards of potential concern. The powders and vapors that have evaporated from the heated binder or from the cleaners can be inhaled if the worker is exposed to the contaminated air. There is also the potential for dermal exposure from contact with surfaces that are contaminated with metal powders, binders, or cleaning agents. Rarely, a binder ingredient, such as certain types of glycol ethers, might be so volatile and pass so readily through the skin that exposure to the vapor might constitute a dermal hazard. Other hazards associated with binder jetting include exposure to hot surfaces. Now we will take a look at the process task by task and demonstrate how the hazards for each of them present and what controls can be used to mitigate them. First, we'll look at powder handling and solution handling. In an R&D environment, or possibly some manufacturing environments, powders may need to be removed from bulk containers and weighed and mixed in the work environment. You can see here the researcher is weighing multiple components into the jar using a scoop and a funnel. It's pretty clear to see the most egregious potential hazards here. the possibility for skin contact and surface contamination. You can see the powder on his ungloved hand and the surface of the scale where it missed the funnel. If this powder had contained a skin sensitizer like nickel, cobalt, or chromium, this could have presented a significant dermal exposure to the researcher. Here in the second picture, you can see the researcher now wearing 2 gloves, transferring all of the weighed powder to a different container. This was in preparation for being mixed in an agitator. However, both of the tasks in these pictures present another potential exposure, one that is more difficult to see. The powders here had an average particle diameter between 1 and 10 microns, a significant portion down in the respirable fraction. And when you shake or disturb powders that fine, they become airborne. So now we have an environment where the hazardous material, the powder, has migrated to the worker's skin, the surfaces of the laboratory, and the air of the laboratory, and he hasn't even approached the printer yet. Now let's talk about getting that powder into and out of the printer. The pictures here were of reclamation after printing, but the process of loading the job box is nearly the same, just in reverse. So to load, the worker takes their powder and pours it into the job box. Since the job box has a larger mouth opening than the containers the powder was stored in, loading is relatively simple compared to reclamation. It can still be a messy, dusty task, though. To reclaim the unbound powder at the end of the run, the worker scoops the powder out of the job box and back into the container. This may entail the use of brushes, scoops, or funnels, as you can see in the picture. Here again, as with the powder mixing and weighing task, this dusty powder presents the possibility for all 3 exposure routes: breathing the dust from the air, getting the powder directly on the skin, or contaminating surfaces, which could lead to ingestion. For this task, unlike the weighing task, the researcher was able to use the downdraft ventilation table, which did a good job of controlling the dustiness of the powder. These were the only 3 integrated samples we were able to obtain for just powder handling. Usually, the task did not involve any mixing or weighing, and it was so short that it was nearly impossible to get a detectable result. Following this run, powder handling was combined with either printing or harvesting. For this run, which did involve mixing and weighing, the results were still quite low compared to the exposure limit for dust. The material was a stainless steel powder. We'll be showing a number of these box and whisker plots to illustrate the data that's been collected for these tasks. The box is defined by the 25th and 75th percentiles, and the whiskers by the 10th and 90th percentiles. So you can see that a data set with a long box and/or long whiskers would have a much wider spread and greater variability than one that has a short box and short whiskers. The powder, which we've discussed, is only one of the materials that need to be loaded into the printer, however. The process also uses a binding agent and materials to clean the print head periodically during a print run. The binders and cleaners can be any of a wide variety of chemicals, particularly the binder, as one of the advantages of binder jetting is the ability to combine different types of powders and binders to achieve different manufacturing characteristics. Typically, especially in a manufacturing setting, loading the liquid materials into the printer presents very little potential for exposure. The bottles are sold from the printer manufacturer, ready to load, and the only thing that has to happen is to remove the top and connect it to the tube that connects it to the printer. In an R&D environment, there's more potential for having to refill bottles without loading a new one, which would present the potential for dermal contact and surface contamination in the event of a spill. Generally speaking, with this task, there is little potential for air exposure, since most of the materials are not very volatile, and this task doesn't require agitating the liquid to the point that it could become airborne. Now, let's take a look at the printing task itself.
It seems like this should be a step with very little potential exposure. The printing area is enclosed with the lid of the printer, and the printer itself is exhausted to this fume extractor unit, which was sold with the printer and is loaded with particulate filters. That is what we originally hypothesized. However, it turned out there was an exposure generation within this part of the process that we didn't expect. The evaporating binder being applied to layers of powder and set with the infrared lamp. In an unfortunate turn of events, the boiling point of the main component of the binding agent happened to be the exact temperature that the infrared lamp was set at, as it set the layers one by one. And that meant that significant amounts of the binder were evaporating during the printing process, first into the interior of the printer enclosure, but then sucked into the fume extractor, where it, being a volatile organic compound, bypassed the particulate filters with ease and poured right back into the work area. It was discovered that air exposure to the binder component, which was a potent reproductive toxin, was significantly above the exposure limit of the substance. You can see from the box plot, where the OEL is represented by the red line, that many of the results exceeded it significantly. Once this was discovered, the use of that binder was immediately discontinued by the laboratory and replaced with more innocuous aqueous-based formulations, an excellent example of substitution. This chart shows the real-time detected concentration of binder solvent during printing. The blue line is the detected concentration, and the orange line at the bottom is the exposure limit. As you can see, the primary component of the binder, 2-methoxyethanol, was detected at concentrations significantly exceeding the OEL. Our integrated results confirmed these findings. Once this exposure came to light, as I said, use of that binder was immediately discontinued, and it was substituted with a less hazardous binder, which the research team referred to as the aqueous binder. These chemicals, 2-butoxyethanol and ethylene glycol, were the primary components of the aqueous binder. You can see that all of the results, even those that did not reach the detection limit, were less than 10% of the compound's respective exposure limits, and with very little variability. The existing local and general exhaust in the lab was quite sufficient for controlling these exposures. We also examined the exposure to powder during the printing task. As was mentioned earlier, the printer has a cover that is closed during printing, and the unit is exhausted to a recirculating air device equipped with HEPA filters. These three data sets are examples of the airborne concentrations of the metal powders used for printing: inhalable chromium, inhalable cobalt, and inhalable copper. The existing controls here were adequate as well for controlling inhalation exposure to the powders. We also examined the exposure to powder during the printing task. As was mentioned earlier, the printer has a cover that is closed during printing, and the unit is exhausted to a recirculating air device equipped with HEPA filters. These three data sets are examples of the airborne concentrations of the metal powders used for printing: inhalable chromium, inhalable cobalt, and inhalable copper. The existing controls here were adequate as well for controlling inhalation exposure to the powders. Now let's examine the task of harvesting printed parts from the powder bed. Once the job box of parts and powder is finished curing in the oven, it is time to remove what are referred to as the green parts from the powder bed. In large manufacturing operations, this may happen within an enclosure and using large suction hoses to siphon off the unbound powder. In the R&D environment, things get a lot more hands-on. For this task, the box of powder was placed in the downdraft table. The researcher used his gloved fingers or spatulas or other lab implements to remove the parts from the powder bed one by one and blow the excess powder off of them using a compressed air gun. This step, which involved deliberately agitating the powder into the air, presents significant potential for exposure. Particularly when not performed in a ventilation hood, which this event was, the blown powder can get into the air, onto surfaces, and onto skin, especially when one uses one's fingers to remove the parts from the job box and hold them to be blown off. It's important to note here that the particle size of the powder and the degree of dustiness that it presents, the potential for agglomeration or clumping and so on, greatly affect the exposure potential. For many commercial manufacturing operations using large-scale binder jetting printers, the powder is ceramic or glass or another mineral material in particle sizes that make them much less likely to become airborne. If you look up binder jetting on a video site, This is more of what you will see. The powders fall more like beach sand and are easily and neatly suctioned up with a vacuum hose, leading to the powder reclamation container. The metal powders used here had much more of a tendency to become airborne. One of the researchers preferred to perform their harvesting on the lab bench rather than in the downdraft table without any local exhaust ventilation. You can see that the results for this were pretty variable, with one exceeding the exposure limit. The researchers' shift exposure to copper did not reach or exceed the OEL because this task only took about half an hour. But these results were variable enough that we would definitely recommend using local exhaust ventilation for this task. Here we can see the datasets for harvesting parts in the downdraft hood. For the specific metal powders, all of the results were below the method detection limit and had much less variability and were all less than 10% of their respective exposure limits, suggesting that the downdraft table was quite an effective control for this task. Things got a bit more variable for the total dust samples, but not by a great deal. We were also able to take a few wipe samples following harvesting. Here again, we have no surface limits to compare these results to, but you can see that in both cases they span at least an order of magnitude, if not more. This suggests that the potential for dermal exposures to these materials is quite variable, which is concerning as many of the components of the powders are sensitizers. This would be a good thing for health and safety professionals to look out for in this type of operation, and start off with a robust housekeeping and contaminant control strategy to try to avoid the buildup of powder on surfaces. The last tasks to examine are transferring parts and materials from one location to another, the sintering step, and the cleaning of the printer. After printing is complete, the printer enclosure is opened, and the job box containing the bound parts and all the unbound powder is moved directly to a curing oven, where the parts are cured until they can be gently handled without breaking. This oven was exhausted to the exterior of the building, but in a situation where the oven vented back into the work environment, this could present another opportunity for even more of the binder to be released into the room. The step of moving the box of powder does not present a very significant potential for exposure since the powder is not being disturbed. Workers would just want to make use of secondary containment and PPE in case of a spill. The last step in actually creating the finished parts is to sinter the green parts until the powder is completely fused. Sometimes this is followed by infiltratings left by the evaporated binder with the secondary metal. By nature of the task, the sintering step involves little to no potential for exposure as long as the furnace is properly exhausted. In order to reach the required temperatures and atmospheric conditions, the sintering chamber must be entirely enclosed and tightly sealed. There may be a slight potential for dermal exposure when placing green parts into the furnace, but once sintering and infiltrating are complete, the object is an article, with no further potential for chemical exposure unless post-process sanding or grinding is required. There may be a slight potential for dermal exposure when placing green parts into the furnace, but once sintering and infiltrating are complete, the object is an article, with no further potential for chemical exposure unless post-process sanding or grinding is required.
The steps that remain in the process are reclamation of the powder for future use and cleaning the printer. While the printers should be cleaned regularly as a good manufacturing practice, this becomes doubly important in any environment where different powders may be used in succession. This researcher was very painstaking and thorough during this step. He used a compressed air gun to dislodge any remaining powder from the nooks and crannies of the equipment, and in the other hand held a suction hose to immediately suck it into the shop vac. At the end, he wiped the interior of the printer down with isopropyl alcohol. This step could also present potential for exposure, especially if the vacuum hose were not used.
This lesson has been created by the Interdisciplinary Training, Education, and Research Activities for Assessing and Controlling Contaminants from Emerging Technologies program, a collaboration of the University of Minnesota School of Public Health, the University of Iowa College of Public Health, and the University of California, Los Angeles Fielding School of Public Health. Funding for InTERACCT is provided by the National Institute of Environmental Health Sciences of the National Institutes of Health. The content of this lesson is the sole responsibility of the developers and does not necessarily represent the official views of the National Institutes of Health.